All right, so in this video, I'm just going to go over a wave review. So we're going to go over wave calculations and which equations to use, the parts of a wave, and then we'll do a little bit on the EMR spectrum, and then we'll also do some conversions as well. So you probably have this worksheet. If not, you can write it down as you go. You can pause, rewind, whatever you need to do. Okay, so we're going to start off with just wave calculations. So first of all, we will give you these constants. Okay, so the speed of light, and we will give you Planck's constant. Okay, so that's something you do not have to memorize. Okay, the things that you do need to memorize are the three equations. Okay, so our first equation is going to be C, which is the speed of light, which we gave you that, is frequency times wavelength. Our second equation is E, which is energy, equals H, which is Planck's constant, which we give you that, times F. And our last equation is E equals, so our energy equals H times C all over wavelength. Okay, so those are the three equations. So the way I remember those is I spell C with a C. So like the word C, as I see something, I do C with a C. Okay, so those are there. So let's see what we need to do. So number one, the wavelength of an EMR wave has we want to calculate the wavelength of an EMR wave that has a frequency of 7.41 times 10 to the 7th hertz. Okay, so what I do is I like to label what I'm given and what they're asking for. So they gave me frequency, so I'm going to label that as F. And we're looking for wavelength. Wavelength is characterized by this upside down Y called lambda. So then I would look which equation uses wavelength and frequency. And that would be this one right here. So that's the equation we're going to use. So C equals frequency times wavelength. So C, which we already know, is 3.0 times 10 to the 8th equals frequency times wavelength. So my frequency is 7.41 times 10 to the 7th. And I don't know wavelength, so I'm going to leave it as lambda. Okay, so I need to get lambda by itself. So this is just algebra now. So for me to do that, I need to divide both sides by 7.41 times 10 to the 7th. So that way these two cancel out. And then we're going to bring it over here. So we're going to divide the speed of light by 7.41 times 10 to the 7th. Okay, so we put that in our calculator. So we get 3.0 to the 8th divided by 7.41 to the 7th. And my answer is I get 4.04858. Okay, so this is where you got to count sig figs. So 3.0 has 2, 7.41 has 1, it has 3, so my answer can only have 2. So remember, you're only as good as your weakest link, so it's the smallest number of sig figs. So I would count 1, 2, draw my line. Okay, and so my answer would be 4.0 meters. So wavelength is meters. Okay, if you use 3.00, that's fine. You would just have 3 sig figs. So I just went off the one they gave us. 2, what is the wavelength of a wave that gives off 5.0 times 10 to the negative 16th joules of energy? Okay, what is wavelength? So I don't know what lambda is. And I know energy. They gave me energy. So I would look and see which equation uses E and wavelength. And then that one would be right here. Okay, so I'm going to clean this up a little bit so I can give myself some room. Okay, so I know I'm using E equals HC over wavelength. Okay, so I know E. So 5.0 times 10 to the negative 16 equals H, which is 6.626 times 10 to the negative 34, times C, which is 3.0 times 10 to the 8th, all over wavelength. Okay, so this is where I see a big algebra mistake usually happen. I'm going to show you a shortcut. If you have a variable on bottom that you want to know, this is all you need to do. Just switch these two. Okay, so you would move lambda over to the left side and then move 5.0 to the negative 16th on bottom. Just switch those two and that will be a little shortcut for you. So what I'm going to do in my calculator is 6.626 to the negative 34 times 3.0 to the 8th. Get my answer, and I'm going to divide that by 5.0 to the negative 16th. Okay, and so I get an answer of 3.9756 e to the negative 10. Okay, so I can only have 2 sig figs based on the numbers they gave me, and that's in my equation. So my answer would simply be, so 3.97 would round to 4.0 times 10 to the negative 10 meters. Okay, a real quick tip is if you're doing the times 10 method in the calculator, please make sure you are putting everything in parentheses. So kind of like how I have it written here, I would keep it in parentheses. Otherwise, you can get your calculator confused on the order of operations, and you can get a completely different answer, even though you have everything set up right. Okay, so please use parentheses. Number 3, calculate the frequency of a wave that has 6.70 times 10 to the negative 20 joules of energy. Okay, so we want to know what is frequency, so that's F, and we know energy. So which equation uses E and F? That would be the one we haven't used yet, which is E equals H times F. Okay, so I'm going to clear this up. So I already know E, so 6.70 times 10 to the negative 20 equals H, which is 6.626 times 10 to the negative 34, all times F. Okay, so again, algebra, I'm just going to divide both. I'm not going to write it this time, but I'm going to divide both sides by 6.626 times 10 to the negative 34 to get rid of it off the F side. So 6.70 to the negative 20 divided by 6.626 to the negative 34. Okay, let me fix my calculator real quick. Okay, and my answer, so I've got a long number. I have 3 sig figs here. I have 4 here, so my answer can only have 3. So my correct answer would be 1.01 times 10 to the 14th power. And frequencies units is hertz. Okay, number 4, calculate the frequency of a light. So I'm looking for F, and I know wavelength. Okay, so that means I'm going to go back and I'm going to use this first equation again. So I'm going to use the C equals frequency times wavelength. Okay, so I already know C, 3.0 times 10 to the 8th equals frequency times wavelength. Frequency I don't know, I'm going to leave it as F. And wavelength is 6.25 times 10 to the negative 7 meters. So divide both sides by 6.25 times 10 to the negative 7th. So 3 to the 8th power divided by 6.25 to the negative 7. Okay, let me check my calculator again. Sorry, I'm having some errors here. So 3 to the 8th power divided by 6.25 e to the negative 7. Okay, and my answer, I get 4.8 times 10 to the 14th power. We're talking about frequency, so my units for frequency are hertz, and so that is my answer. Number 5, calculate the energy. So that means we're looking for E from the violet light given off with a frequency of 8.23 times 10 to the 12th. Okay, so all this inverse seconds is right here that's the same thing as saying hertz. That's just another unit for frequency, so don't get hung up on that. Okay, so we know F and we're looking for E. So that means we're going to be using the E equals H times F. Okay, so E I don't know, so I'm going to leave it as E. H, 6.626 times 10 to the negative 34 times my frequency, which is 8.23 times 10 to the 12th. Okay, so we're gonna put that in the calculator. So 6.626 to the negative 34 times 8.23 to the 12th power. Okay, I have 4 sig figs right here, and I have 3 right here. So that means my answer can only have 3. So my correct answer would be 5.45 times 10 to the negative 21 joules. So the unit for energy is joules. 6, what is the energy of a light wave with a wavelength of 8.10 meters? So we're looking for E, and we know wavelength. So that means we're going to use that last equation, the E equals hc over wavelength. So E I don't know, so I'm going to leave it as E. H, 6.626 times 10 to the negative 34 times, let me go ahead and move this wavelength out of the way, times C, which is 3.0 times 10 to the 8th. Sorry, that was a horrible 8. All over my wavelength, which would just simply be 8.10. Okay, so we're going to type that in our calculator. We're going to see what we see. So 6.626 to the negative 34 times 3.0 to the 8th. Get your answer, which would be 1.9878 times 10 to the negative 25th. Then we're going to divide that by 8.10. Okay, so I have 4 sig figs for my H, I have 2 for my C, and then I have 3 on bottom, so my answer can only have 2. So my answer, we got 2.5 times 10 to the negative 26 joules. Again, if you use 3.00, that's fine. You would just have 3 sig figs instead of 2. Okay, so those are the equations. So those are the 3 equations you need to know. So it does help it helps me to label what they give you and what you're looking for, and that will tell you which equation to use. Okay, last thing on this page is labeling the parts of a wave. Okay, so A right here, the top of a wave is called a crest. Okay, B, the bottom of a wave is called a trough. So the way I remember that is if you have any livestock, when you throw food into a trough, that's what they eat from. It just basically looks like half a cylinder. Okay. C, this is going to be wavelength. This is very important to know. Okay, one wavelength. Okay, so one wavelength has to have one full crest and one full trough. So one full crest and one full trough. Okay, so it started at the top of a crest and it ended at the top of a crest. Okay, so if I were to add this crest up and this crest up, that would equal up to one crest, and this is one full trough. Okay, so that in order for it to be a full wavelength, it has to have a full crest and a full trough. Okay. For part D, the distance from the middle point to either the high point or the low point, this is just called amplitude. So amplitude. Okay. Next thing, we're going to EMR. So real quick on EMR, I'm going to kind of just erase some of these things. You can rewind it if you need to. I'm going to erase some of these so I can make some room to go over the EMR stuff. But feel free to rewind it if you need to see that again. So EMR waves. So we have radio. Then we have micro. Then we have infrared. Then visible. Then we have UV. Then X-ray. And then gamma. Okay, so the way sometimes people remember this is real Martians invade Venus using X-ray guns. So you can come up with your own sentence if you want to, but that's just one that we kind of use. Okay, so radio is going to have the longest wavelength, so a long wavelength. Okay, and gamma is going to have a very short wavelength. Okay, radio, this left side is going to have a very low frequency. Gamma is going to have a very high frequency. Okay, so frequency is the number of waves in a second. So you got to think, if you have long wavelengths, you cannot fit as many waves in 1 second. If you have short wavelengths, then you can fit more in 1 second. So that's frequency. Okay, radio is going to have very low energy. Okay, gamma is going to have very high energy. Okay, because you got to think there's radio waves all around us. If they were very high, if it was high in energy, it would be hurting us. Cell phones use microwaves and stuff. So if that was very high energy and that was around us all the time, that would not be very good for us. Okay, so then we have our visible lights. We're going to break that down. We have our colors. We have Roy G. Biv. So red, oops, let me fix that. Red, orange, yellow, green, blue, indigo, and violet. Okay, so Roy G. Biv, so remember that. So those colors follow the exact same pattern as our EMR waves. Okay, so red is going to have very low frequency, high wavelength, low energy, and then violet's going to have shorter wavelengths with higher frequency and higher energy. So it's going to follow the exact same pattern from left to right. So number one, what happens to the energy of an EMR wave if you double the frequency? Okay, so our equation that deals with frequency and wavelength is C equals frequency. Oh, I'm sorry, that's number 2 we're talking about. So let me fix that. So we're talking about E and we're talking about F. So we know our equation E equals H times F. H never changes. Okay, so if H never changes, just for this sake, we can mark it out. So if frequency were to go up, energy goes up. So you got to think of, if I can fit more waves into a second, that's going to be a lot more energy. Okay, so that's why gamma is very dangerous. It has a large amount of waves in a small amount of time. So that's a lot of energy. So if frequency goes up by 2, energy will go up by 2. So this is called a direct relationship. One goes up, the other one goes up. One goes down, the other one goes down. Number 2, now we're talking into the C. So I want to triple my wavelength of an EMR wave. What specifically should I do to the frequency of this wave? Okay, so we're dealing with wavelength and we're dealing with frequency, which is C equals frequency times wavelength. C never changes. Okay, so in order to keep C the same number, if one goes up, so if wavelength goes up, frequency has to go down. Okay, so they have to go in opposite directions. So if my wavelength wants to go up by 3, my frequency should actually go down by 3. So I would actually divide by 3. Okay, this is called indirect relationship. So if one goes up, the other one goes down. So you got to think about frequency is the number of waves. If my wavelength gets longer, I can't fit as many waves in that second. Okay, so that's an inverse relationship or an indirect relationship. Number 3, rank IR, violet light, and FM radio in order of decreasing wavelength. Okay, so my wavelength is getting smaller. So if my wavelength is getting smaller, that means we are going from left to right on my scale, on my EMR scale up top. Okay, so we would start from the left and go right. So radio would be the furthest thing on the left. So we're going to put radio. Then the next one that we're going to the right would be IR. And lastly, violet light would be under that visible category. So my last one would be violet light. Okay, so that is decreasing wavelength from left to right. Number 4, rank UV, orange light, microwaves, and gamma in order of increasing frequency. So increasing frequency also goes from left to right. Okay, so we're going to rank it from left to right. So the furthest thing out of my list on the left is going to be micro. Okay, now we're gonna start going right. So my next thing I could pick is going to be orange light, followed by UV. Then it's gonna be followed by gamma. Number 5, rank IR, UV, green light, gamma rays, and indigo light in order of decreasing energy. So decreasing energy goes from right to left. Okay, so remember, radio waves are all around us. So if they had high energy, we'd be in a world of hurt. Okay, so energy is going to decrease as you go right to left. So we're going to start at the right and go left. So that means gamma is going to have the highest energy. Then I'm going to see what's next. UV would be my next one. Then I'm going to look at my indigo light and green light. So which one is further to the right? That would be my indigo, followed by green. And lastly, the furthest thing on the left would be IR. Okay, so please rewind that if you need to watch that again. You just need to know your EMR scale, and when it comes to ranking wavelength, frequency, and energy, which way it goes. Last thing is just a little bit of conversion, so this should be review. So this is how I do it. So if you have a different way, if you count decimals, that's fine. Okay, you will need a metric scale for these if you're practicing these on your own. So the way I do this is we're going to start off with what's given. So convert 456 nanometers to meters. So I'm going to start off with 456 nanometers. Okay, and we're trying to get to meters. So I'm not even going to worry about numbers yet. The first thing I need to do is I need to put nanometers on bottom. If they are not opposite of each other, on top and bottom, it will not work. Then I put meters on top. Okay, so the way I do this is I determine which one's bigger, and I'm going to set it as 1. So meter is 10 to the 0 power. Nano is 10 to the negative 9. So that means meter is going to be my biggest one, so I'm going to set that as 1. Then I would count how far it takes me to get from 0 to negative 9, which would be 9. So this would be 1 times 10 to the 9th power. Okay, so if you do it my way, and you set the biggest one as 1, okay, your power or your exponent will always be positive because you're counting going to the right. So now all we have to do is just take our top numbers and multiply it. 456 times 1 is just simply 456. Then we're going to divide by the bottom number. Okay, so 456 divided by 1 times 10 to the 9th. Okay, and this is going to give me 4.56 times 10 to the negative 7 meters. And that's it. These are just one-step problems, so try not to make them more difficult than they are. So number 2, how many megahertz are in 565 hertz? So again, start off with what you're given. So 565 hertz, which is Hz. Okay, and we're trying to get to megahertz. So first thing I'm going to do is I'm going to put Hz on bottom, and then I would have to put megahertz on top. Okay, so if you do not see a prefix before that hertz, that means that is a base. Okay, so that would be a 10 to the 0 power. Okay, so if you don't see a prefix, that means there's a base. Mega, if you look up mega on the scale, this would be 10 to the 6th power, so 10 to the 6th power. So I would see that megahertz is definitely bigger, so I'm going to put 1 on top. So 1 megahertz. Then I would count how many spots it takes to get me from 10 to the 6 to 10 to the 0, which would be 6. So this would be 1 times 10 to the 6 on bottom. So that means we're done. All we got to do is our math. So 565 divided by 1 to the 6th power. Okay, and I get 5.65 times 10 to the negative 4 megahertz. Again, if you have a different way, if you count decimals, that's fine. This is just the easiest way because you will see dimensional analysis a lot more, so this just gives you practice in doing it. Number 3, how many nanometers are in 2.3 times 10 to the negative 2 meters? So 2.3 times 10 to the negative 2 meters. First thing I'm going to do is I'm going to put meters on bottom. That means nanometers has to go on top. So I would look, first I need to look at my metric scale. Meters is a base, so that's 10 to the 0. Nanometers is 10 to the negative 9. So you definitely see that meters is the biggest, so I'm going to put 1 on bottom with meters. Then I would count from 0 to negative 9 would be 9. So this would be 1 times 10 to the 9th up top. Okay, so this is where you got to know that the past two, we always put 1 on top. So just don't assume that 1's always going to be on top. It's just going to follow whichever one's the biggest. So now, all we do is we just multiply whatever's on top. So we're going to take 2.3. So 2.3 to the negative 2. And we're going to multiply that by 1 to the 9th power. Okay, so two answers you can get this. You can do 2. Okay, so we've got a lot of zeros here. Okay, so you can write it out that way if you want to. If we ask for scientific, you would need to convert that. So you would start where the decimal would be. It would be 1, 2, 3, 4, 5, 6, 7. So we're going to stop right before that last number. So this would be 2.3 times 10 to the 7th nanometers. Oops, let me clear that up real quick. Either one is fine. You just need to know how to go back and forth between the two and depending on what we ask. Last one, 4.5 times 10 to the 5th terahertz. Okay, so I wrote down what we started with. Terahertz has to go on bottom, and then megahertz would go on top. So you look at your metric scale. Terahertz is definitely bigger than megahertz, so tera is going to be 1. Okay, so let's write out our powers. So mega is going to be 10 to the 6th. Okay, tera would be 10 to the 12th. Okay, so I would count how many places it takes to get me from 12 to 6, and that would just be 6. So 1 times 10 to the 6th would be on top. And now we're done. So now we just got to multiply whatever's on top. So 4.5 e to the 5th times 1 to the 6th power. Okay, and I get 4.5 times 10 to the 11th megahertz. Okay, so hopefully that kind of helped you out as far as waves, EMR, and conversions. So feel free to rewind this if you need, and hopefully this kind of cleared some things up for you.